que é o seguinte, então essa aula ainda a gente vai revisar algumas coisas do non-interacting, do weakly interacting electron gas related to the calculations that we did last time. So this is one more lecture, and then on Wednesday we start with another big chapter, which is the effective theories. Okay, so this will then be, so what we did so far is perturbative analysis in terms of diagrammatic perturbation theory. So here we had one example for the weakly interacting electron gas where we managed to actually sum a whole class of diagrams to have an infinite series, summation of an infinite series of perturbations here in a certain approximation which used that we are considering high density electron gas, which is equivalent to saying weakly interacting electron gases. And we managed to find a closed expression for the free energy, keeping a certain class of diagrams, which is so-called RPA approximation. So then after the lecture, we will see that this diagrammatic analysis, like where we identified certain building blocks, which are the building blocks we can build up all relevant diagrams of, that these building blocks actually can motivate us to introduce some effective theory where the diagrammatic building block then is represented by some bosonic field. And this is known as the Hubbard-Stratonovich transformation. So we will discuss this in quite general, and then revisit this example of the weakly interacting electron gas using this idea of the Hubbard-Stratonovich transformation. And as said, it would be good then to have another example which would be related to magnetism, and which probably is like 3 more lessons. Okay, but first we should close the story. And so one thing that we said when we started looking at the perturbation theory in weakly interacting electron gas, that actually when we looked at the first order correction to the free energy, from which we could then also calculate the density of states, we saw that there was some problems happening in the density of states that we found perturbatively in low order perturbation theory, because according to our result, what we had found there was that the density of states at the Fermi level would actually be 0, which doesn't really make sense, because this would mean that all the transport property and everything would vanish. But we also saw that this was related to some log which appeared due to the long-range nature of the Coulomb interaction, so 1 over q squared potential. So now we managed to actually go beyond low-order perturbation theory and actually to manage to an infinite series. So let's see if this problem that we encountered is repaired by the better analysis that we did. So this is what we look at now. So the question, does this RPA, the random phase approximation, repair the, well, strange result that we found for the density of states for low order perturbation theory? So does RPA repair the pathology in Fermi surface density of states? So the density of states evaluated at the Fermi surface. So to answer this question, let me just recall some basic things, which is, well, we have calculated the free energy in the RPA approximation. So from the free energy, we can always calculate the particle number by taking the derivative with respect to the chemical potential of the free energy. This is the particle number, you know, from statistical mechanics. Now, if we take a second derivative of the particle number with respect to the chemical potential, we arrive at the density of states, no? So this is the thermodynamic density of states. Called nu, derivative of the particle number, or second derivative of the free energy. And that was the object that made some problems in low order perturbation theory. So let me just recall this, that in first order, what we had encountered was the free energy given by sum here over the 4 momenta. Then we have here the product of two Green functions, which this is somehow what we define the polarization operator, and then the Coulomb interaction, the long-range Coulomb interaction. Now, taking this result here, and then taking the first derivative, we find for the particle number following. And I'll just explain where this comes from. So let's just see where this comes from. So let's make some diagrammatic picture for the particle number. So up here was the free energy, which is something like two Green's functions and an interaction potential. Okay, P and P plus Q. Okay, so this is like a diagrammatic representation of the first correction to the free energy with this wiggly line, the interaction line. Now it's convenient to also represent the number operated, or the number of particles diagrammatically. Well, what we have to take is the derivative of the free energy. Okay, so the derivative with respect of the Green's function with respect to the chemical potential, so this is 1 over P squared minus mu plus E epsilon n, just gives minus GP squared, no? So this is just because we have 1 over mu, and so if you take the derivative, you get it squared here. So we can represent this particle number where we have to take the derivative with respect to the chemical potential by just noting that, well, if we act with the derivative, let's say on this Green's function here, we just reproduce the initial Green's function and get another one. Okay, so we can represent this here just by some. It's better just by some dot, which tells you, well, instead of having one Green's function, we have here two Green's functions. Okay, so this would be a diagrammatic representation of the particle number. Now, the second contribution would be where the dot is on this line here. So we would have just the GP plus Q squared. But then we can symmetrize this expression using that the potential is an even function of Q. No? So just shifting P by P minus Q and then Q plus to plus Q, you get factor 2 for the two possibilities of taking the derivative here or here. So this is factor 2, and then we arrive at this expression here. And well, let's see. Well, this then is the particle number, and then we can take a second derivative, which is just, diagrammatically we can represent again by taking another dot. And what we saw is that this then had the pathology that it would vanish at the Fermi surface. So that was like a problematic part. Okay? So this is just all in first order. Okay? Now let's see how all this changes if we look at the RPA. Okay, and then just taking another derivative. Okay? So in RPA, what we start out from is the free energy that is written on the right hand side, and I just repeat here RPA T half okay, where this is a polarization operator, so we see if we linearize this in Q, you get exactly this expression given here, P of Q, and then we have the polarization operator, which is sum over P, GP, GP plus Q. Okay, so if we now take the derivative, we get the particle number in RPA, and if we do so, we have to take the derivative of the log, and and then the derivative of the polarization operator, which was what we did here, which gave the product of Green's function squared in GP. So if I do this, what you arrive at, okay, let's make it in 2 steps. So this is from taking the derivative and then of the log, and then we have here the derivative of the polarization operator. Okay. So now what we see here is that this is actually structurally identically to this expression here, because this we could have also written as a derivative as a potential V of Q times the derivative of the polarization operator, which is this expression here. Okay, so you just notice here, there's leave some space, that the derivative of V of Q is given by the sum over P squared GP plus Q. And there's the factor minus 2TLQ. And there's a second contribution from Q minus Q, which we here put into the factor 2 due to symmetrization. And okay, so what we see here is that in the RPA approximation we arrive, so if you plug this in here, at the identical result as here. The only thing is that instead of having the Coulomb interaction potential, we have here some effective potential, which I call F of Q. Okay? So if we draw the diagram for the particle number that we drew here, well then what we have is again such a bubble where we have, let's say, active on the Green's function here above on the Q plus Q, P, then we have here the Q plus Q. And now the interaction line, instead of just taking the wiggled line, just take a, it should be some fat wiggled line. Okay, let's try to make this better. This is just a wiggled line. And this here is some fat line, which is representing here the effective interaction potential. Okay, so we see that in RPA approximation what actually happens just is that the potential that we had was their Coulomb potential is substituted by an effective potential. Okay? This effective potential is described by this expression here. So let's just see how we can understand this effective potential. Well, we can just, if we like, we can just expand this, let's say here in the potential, and get some infinite series, okay? So if we do so, we get a series where now this here just comes from the denominator, and then we just continue getting more and more powers of this, okay? So E of Q and so on and so on. Now, this can be actually rewritten in a self-consistent way, in a self-consistent equation, in the following way, where now the dot dot dot, so which are all the higher orders, are just accounted for by noting that once you look at this contribution here, which come afterwards, this corresponds to substituting here V by the effective potential again, no? So there's a self-consistent equation which the effective potential fulfills, okay? Let's just dividing this. Now, of course, if you now solve this for the V effective potential, well, you just arrive at this expression here, okay? So this is just some reformulation, where just a trivial reformulation of this expression here, but this is done to try to explain light diagrammatically this wiggled line, this fat wiggled line. So if we look at this diagrammatically, this would be the effective potential, representing the effective potential, and this is given by just the bare Coulomb potential. Then we add the bare Coulomb potential. Then we have this polarization bubble, bare Coulomb potential plus and so on. Okay, so these dots correspond to having higher and higher orders here of these polarization bubbles. Okay, and the last line here, which is the self-consistent equation, is just rewriting this equation in the following form. So we have here the polarization bubble, and then here actually again the full effective potential. Okay. Now this is, again, I think quite nice, because now this is more intuitive, because we see what happens. So as said, if you compare the first order with the RPA for the particle number, it's the same diagram, only the potential is substituted by this effective potential, which now is, well, it's a bare Coulomb interaction, then it's a bare where we create electron-hole pairs, one electron-hole pair, two, and so on. And what they actually represent is just electron-hole pairs which start, which express the polarizability of the medium that we are in. Okay, so we are not considering interactions in vacuum, but we are considering interaction in the Fermi sea, where if there is a potential, the electrons will just readjust and try to screen the potential. Okay, so this corresponds to the picture that we had. Well, if you have two charges, they don't just interact barely with themselves, but in polarizable medium, they will form some dipoles which screen the charges. Okay, here as well. Okay, and these dipoles here just correspond to the polarization bubble, no? Because we said, well, you can imagine this is a Fermi sea, then this corresponds to creating a hole and an electron. Okay. So these are little dipoles which we can create and which start to screen the charges. So they're screening the interaction. Okay? So the effective potential that is substituted here for the bare interaction just is exactly what we said in the beginning. Well, there is a problem in the first order interaction. Correction to the density of states, but we saw that this was a logarithm, came from a logarithm which actually could be related to the 1/q² potential. Okay, so that was the long-range nature of the interaction. Now, what we see is if we go to higher orders, we see, well, we are considering here weakly interacting electrons in a dense medium. Okay, so it's not the vacuum, but there's many more electrons around which should screen the interactions. And this is exactly what we find from the RPA approximation, which is in the high density limit, and where we saw that the only relevant diagrams are exactly those which account for the screening. Okay? So in the RPA approximation, which holds in the high density limit, we saw that the main effect that we have to consider is exactly the polarization of the medium, which means that the interaction between the electrons is not the bare interactions, but it's a screened one. Okay? So we see then the number of particles is represented by the same diagram, now by in a way regularized interaction potential, which we'll see like in a minute is now not long range anymore, but is actually short range due to the screening. And then of course this should resolve our problem here. Okay? So that's the idea. Here now we can make this a bit more formal. Let's see. By recalling some things. Yeah. Okay, so that's the main idea. So let's make this a little bit more formal. But I mean, this idea is clear, yeah? Okay, let's just rewrite again the effective potential that we had if we solved the self-consistent equation, or just one that we found. This expression here. This is a four momentum, no? That's the three momentum, this depends also on the frequency. And let's rewrite this in the form that you should recall from electromagnetism, where we introduced here the epsilon of Q, which again is a four momentum, which is 1 minus potential times the polarization, and this is the electric function. Okay. So structurally, first make a few observations, and then recall some things about the electric function. The particle number, the RPA approximation, is the same as first order expansion. What you get from first order expansion in the interaction. There's one important difference, only with the bare interaction being replaced by effective interaction. Where, as we said, the effective interaction is screened by electron hole bubbles or electron hole pairs, which are the polarization bubbles. Which we refer to this building block diagrams that always appear, no? So this means that if we address, we saw this already here, the problem that we posed in the beginning, what is the free energy of the weakly interacting electron gas, that the full complexity of the problem, which here just reflects in the polarization of the electron gas at finite density, and all this problem is stored, or all this information is stored in the polarization operator. Okay, so this knows about everything that we're interested in. So the full complexity of the polarization of the homogeneous high density, so this is where the RPA approximation holds, electron gas is then encoded in this polarization function, which is also known the Lindhard function in the literature. So we can form the integral or the summation over the momentum P normalization operator, you can just write it once explicit, so this depends on the three momentum and the Matsubara frequency. One can do this summation. I think it's an exercise on the new list to do this, and then one arrives at following expression here. I think I have written this down already once, no? Minus VFQ, where VF is just the Fermi velocity, no? Fermi velocity, and Q is the absolute value of the momentum. And the nu zero here is the density of states at the Fermi level. Can you read this? So this is I omega m, which is the Matsubara frequency, over VFQ. So all this depends on the ratio of omega m divided by VFQ, which is dimensionless. So this is an I omega m over VFQ, and then you have I omega m plus VFQ divided by I omega m minus VFQ. And this is known as the Lindhard function. So this is an exercise, and equivalently, this is all stored in the dielectric function, 1 over minus VFQ times this Lindhard function. So if one wants to see the effects of the polarization, one has to study this function here, okay? And we can study this in two limits, so everything depends on the ratio of omega m divided by VFQ, okay? So this polarization depends on the three momentum Q and the bosonic frequency. So you have, in a way, because you have a velocity given in the problem, which is just the velocity of the electrons, the Fermi velocity, the velocity of the electrons at the Fermi surface. So you have two scales in the problem. You can convert, if we want, this here in a time scale or this in a length scale. Okay, so we have two length scale. Let's say Q denotes like the modulation of the function. This is the inverse of a length scale, so this only depends on the absolute value of Q. So this is defined in inverse length scale, which tells you about like an inverse length scale of, let's say, the modulation of the potential here. And then we have related another length scale, which is the Fermi velocity times the typical time scale. We have time scale, let's say the electrons have to react to an external perturbation. So this defines also the length scale, Vf times 1 over, let's say, the frequency defines in time. So you can compare these two scales, okay? So you have, let's say, make some modulation to the external potential, and then you can have, or like consider the long time limit where electrons always have enough time to adjust to this perturbation. So this would correspond to long time scales or small frequencies. So the omega to 0 limit. So where always electrons are rapid enough to account for the modulation, and we will see that here's then the screening that we're interested in. But you can also consider the opposite limit where, well, the time scale is just shorter, okay, so that they cannot always immediately adjust. Okay, so there's some, let's say, due to the Fermi velocity, you can compare here to time scale, so there's two limits. One can, for example, study this function, namely omega m being larger than VFQ or smaller than VFQ, corresponding to the limits that we're using. So this we can look at, but let me just recall here some basic stuff about the electric function, so we can understand what we said here about the polarization and the screening that is going on. This is just a small reminder. So recall that the electric field polarizable medium is related to the vacuum field. Vacuum field D through the dielectric function Q omega, that's Q omega, where epsilon Q omega, the dielectric function, can be expressed as 1 plus 4 pi, and then we have chi, which is the electromagnetic susceptibility of the system. By the electromagnetic EM electromagnetic susceptibility, which measures the tendency of the medium to adjust to an external perturbation. External electromagnetic perturbation. So here we see, just by comparing, well, the effective potential is the generates the electric field that we are interested in. So, I mean, then you arrive at the relation that you find here. So the epsilon we expressed here, which means that in our case, the electromagnetic susceptibility is just proportional to the polarization. Okay, so this polarization operator, or if you calculate it, so this is, of course, depends on the dimension that you're in, the result. So this result here, the Lindhard function, is the result in 3 dimensions. Okay, and the electromagnetic susceptibility is just proportional here to the polarization, or the Lindhard function. Okay? So this is just something from electromagnetism. Okay, so that's the story. Now let's just do the 2 things that I said, like this Lindhard function depends on the ratio of these 2 length scales. Let's consider like 2 interesting limits and see what happens, and then this closes the section here on perturbation theory when it comes to the effective theories. So let's just evaluate Lindhard function 2 regimes. So Lindhard function ratio of I don't know if this is the most, let's write it. Like how I said it, like on the ratio of the 2 length scales. This is a length scale and this is a length scale. Okay? So it depends on the ratio of these 2 length scales. This would be wavelengths here spatial variation of potential that you're applying or you're looking at. And this here is, let's say, the distance. And excitation that is formed from electrons and holes from the Fermi, as close to the Fermi surface. Excitation. Excitation propagating with the Fermi velocity can distance and excitation. Propagating this Fermi velocity can travel in the time set by the frequency 1 over omega. Okay? So we can look at two limits, which are on the one hand a very long time, or the static limit, where the excitations always have enough time to adjust to any perturbation. Okay? This is the static limit. Where this time is much larger, where this length, the excitations travel is much larger than the length scale which you have the perturbation. So this limit, the electron gas has always enough time to adjust to spatial variations. Scale 1 over Q of the potential. And this U means actually to adjust, means here, as we said, well, the electrons, the holes will just screen the potential, no? So here, this means to screen out. Locally, the electron neutrality violation that is put into the system by variation, spatial variation of potential. Violation or violating potential fluctuation. Okay, so we should see in this limit some screening going on, and this can be seen in the formula that if we evaluate in this limit the Lindhard function, then what you find is following, that this just gives you the constant minus μ0, because yeah, so we saw we had in the log we had just always the two terms compared. Now we have Q and omega. So if we said omega, if we neglect omega, the log was just the argument of the log was just 1, and vanishes in here like this minus 0 plus order omega over here Q, which here in this limit is assumed to be small. So this implies that if we now plug this into the effective potential, it's not there anymore, but if we take this value, well then the effective potential now, before the potential just depended on, okay, still in this limit just depends on the momentum, not on the frequencies, because we take the static limit. So this is given by 1 over b to the minus 1, the bare potential, and then we have here plus μ0, and this can be rewritten if we recall that this here is q squared over 4pb squared, then we can rewrite this as 4pb squared divided by q squared plus 4pb squared to 0. Okay? So if we recall, well, if we set this here 0, well, then of course we just reproduce the bare potential. So what happened through the looking at the interactions in a dielectric medium in the static limit, well, we see that the former, like let's say, massless bosons now became a mass. Okay, so this is like the interactions now are screened. So this means that the former massless bosons, which communicate interactions, are now not massless anymore, but obtain the mass, which makes the interaction then short range. Okay, so if we like, we can call this here an inverse length squared, which is the Thomas-Fermi screening length. Okay, so the lambda that we introduced here, which is 4p b squared to 0 to 1/2, is known as the Thomas-Fermi screening length. Okay, so if you just do the Fourier transform of this potential, instead of having a 1 over r potential, you will find that this is now given by minus p squared over r, but then you have the exponential screening on long length scales. And the length, of course, is given by the Thomas-Fermi screening length. Okay? So, through the polarization of the medium, the interaction became a short range or exponentially screened potential. Exponentially screened. And just to make once more the picture, so we have drawn this a couple of times, but just to make it once more. So we have this electron, let's say, in some dielectric medium, and this will make just that the medium will try to react to this inhomogeneity introduced into the charge neutral medium, so to re-establish like the charge neutrality, so it tries to polarize it here to compensate the negative charge that's created here locally. Okay. And the long length scales, this will just then lead to complete screening, meaning that the potential here should decay, actually exponential decay on a typical length scale, which depends here on the density of states of the Fermi sea. So the higher the density of states, the shorter will be the length scale on which the screening happens. Okay, so now given this and all the discussion before, that this problem that we encountered in the density of states from first order perturbations here was a log, which was related to the 1 over q squared. Well, then one can see this should just then cure the problem that we had encountered for the density of states. But who likes can just move into this, but just mention this then. So if we take the second derivative of the free energy and look then at the density of states, one sees that Thomas-Fermi screening repairs the problem that we encountered in the first order expression. DOS lightness states, which had its origin in Q squared singularity. Singularity of long range lunar interaction potential. Okay, so this was the one story that I wanted to just discuss to finish this, and then the second thing that then is just very just superficially, but we will see here at this example also another limit. So this was like the static limit where we always gave like the electrons or electrons and holes, the excitations, enough time to react to whatever modulation put in on the length scale set by the wavelengths 1/q. So in the other limit, where the electron gas does not have enough time, so there's appearing something interesting that I just want to briefly mention. So there's some instability, and this then is just mentioned, and this is something like which is interesting because this will then also be something that actually try to come up with some general scheme how to address like whatever problem you have. Like here we have the weakly interacting electron gas problem, where we just start off and let's do some perturbation theory around some non-interacting reference state unit. But this might not always be the right thing to do, and this is actually signaled sometimes in instability. So that's why I just want to mention here briefly instability, and we will see that this is something that actually happens more often, and this is also something that motivates to then do something more systematic or different than what we did when we do a perturbation theory around some non-interacting reference point, because this does not always have to be the right thing. Okay, so this is more kind of motivation. Plasmon mode, which is a corrective instability for weakly interacting electron gas. Okay, and this actually just has to deal with evaluating the Lindhard function. Again, the 3D in the opposite limit. Where now we look not at very small frequencies or long times, but at large frequencies or short times. And short here compares to 1 over VFQ. Okay. So if you evaluate the Lindhard function and plug in the value into the effective potential, let me just write the result, what you find. For the effective potential, which in this limit now is not anymore static, but also depends, so it's dynamic, depends also on Matsubar frequency. Then you find the following. So there's an omega p, which is a Plasmon frequency, which I will define in a minute. So this is divided by omega m squared, and the Plasmon frequency omega p is 4p m squared m, where this is called plasma frequency, where the n here is just the density of the electron gas total number divided by the volume, which here turns out to be 2kf, or kf cubed divided by 3p squared. Okay. So this is just, if you evaluate the Lindhard function in the opposite limit, well then there appears a ratio of q squared over omega m squared with some number here, or actually it's not a number, it has dimensional frequency, which is written here, and then you can just rewrite this, if you plug this then into the expression for the effective potential, then you can just put out the 1 over q squared here, and end up with this expression here, okay? So now, I mean, this is just, again, this is just to motivate, like, also what we are going to do afterwards. So this is the effective potential, which now is dynamic, so it depends on Q and also depends on the frequency, but this is the Matsubara frequency. Well, this is something we never discussed very carefully, but I mean, we have an idea that there's some always, or we have to look at, but the idea is that in many cases one still needs to do an analytic continuation from imaginary to real frequency. So we haven't discussed this, we have seen this in the past in tools sometimes, and there's a systematic way, like if you look at correlation functions, how to do this, and I mean if there's a continuation of this course, maybe we are going to discuss this there. But let me just state here that sometimes it's just really substituting I omega n for some real frequency, okay, or omega n by I omega where omega is real. Now if we do here this kind of analytic continuation, so substitute this omega n by I omega, omega is real, well then we change the sign here, okay? So if we do the analytic continuation, just do it now here in the blackboard, because this is all very, I mean, just qualitative to give some motivation. So on analytic continuation, I omega m substituted for by some real omega, well then we would just here change the sign, no? So what we see here then is something interesting going on, namely if this frequency matches the frequency of the intrinsic frequency of the system, which is the plasma frequency, just depends on the density of the electron gas, we have some instability going on here, okay? So there's something exploding. So let's just see like the physical picture where this instability comes from. So let's first notice there's an instability of the weakly interacting electron gas in this limit. Weakly interacting electron gas. Then we have the external frequency of the perturbation being given by the Plasmon frequency, okay? So this, the Q and the omega correspond to the, let's say, the wavelength on which you do an external perturbation of the frequency. So if this matches the intrinsic frequency, you have some instability going on. So let's just try to see what this corresponds to. So this is the Plasmon mode. Just give some argument. Recalling that this is in a limit where we are considering frequencies or times which are shorter, such that the electron hole excitation is not, as in the static limit, always have enough time to completely adjust to a perturbation done to the system, okay? So this is like the way they are running behind the perturbation that is done. Okay, so let's just imagine the following. So imagine the electron gas that we start out from, which is charge neutral because it's used several times. It's on some ionic, positively charged ionic background, which compensates for static component. So the Q equals 0 component of the potential we always set is 0. So imagine all this electron gas being uniformly on the positive background, being uniformly displaced by some distance, let's call it x, against the positively charged background. Positively charged background. So let's make a sketch what I mean. So in the beginning, we have our electron gas just uniformly covering the entire, let's say, system. So down here are the positively charged ions, and on top of that is the electron gas. And now let's consider the situation that we displaced the electrons just by some distance x here against the positively charged background. Okay, so this is still, say, positively charged background, but now we have displaced here the electron gas against the background, meaning we have here a surface layer of negative charges and here just a surface layer of positive charges. Okay, so we started from the system ionic background, electron gas, and just displaced it by some distance x. Okay. So what happens there is we have formation of oppositely charged surface layers, the negative and the positive ends. Ends of the system. And actually the surface charge density, surface surface charge densities are just given by rho plus minus E, then the density times the x of the displacement. And these lead, so you have the two charge densities here, which are proportional to the displacement x, and this in a way just makes your problem to one-dimensional problem, if you like, or like a plate condensator, so there's some electric field inside the system. So this leads to an electric field. Which is proportional to the surface charge density, so it's proportional to x, and it's well directed against the origin which created it, so it's directed opposite displacement vector. Okay, so this is just exactly like in a plate condensator, like you calculate the electromagnetism. So just you have the constant electric field due to the surface charge. Okay, just by Gauss law already like. So this means then that the electrons inside the wire, inside the system, in the bulk, will feel a force. They are exposed to the force, to the corresponding force, minus 4p x. And if you look then at the equations of motions, you have to solve, well, just very simple, Newton's law. So the solutions of this equation are then, so you have here, well, you expect dynamics only in the x direction, so let's call this the x direction, everything else is dead. So you have a one-dimensional problem, well, and second derivative should reproduce itself, so you get some oscillating solution, and the oscillation frequency is just given by this expression here divided by n. Okay, so you get some oscillation in the square root, so you get an oscillation given by the Plasmon frequency. Solution oscillates at omega p So this means that you find here actually like a harmonic oscillator problem. So the electron gas will just oscillate, then it will build up again here surface charges, and it will just keep oscillating. Okay, so you have a collective movement of the electron gas which oscillates at this internal frequency. Okay, so if you perturb the system exactly at the resonant frequency, well, you have an instability. Okay? So this means that this instability that we just found here, we can, I mean, just by in simple terms, relate to a collective movement or a collective oscillation of this weakly interacting electron gas. Okay? So there's some collective excitation going on here, which is reflected in the singularity of this susceptibility or the Lindhard function. Okay, now what this, we don't go into detail here, but I mean, if you want to generalize, this is what we will now do, is we will, like in the next lecture, then see how to go to effective theories. And it's always like one thing we should recall here, which is, well, what we did is we said, let's try to understand the weakly interacting electron gas. And what we did is just say, let's say the non-interacting electron gas is a good reference point, and just do perturbations here around. And it turned out that, in fact, we can, in the high density limit, just resolve we can just some infinite series of diagrams to find the free energy. But this doesn't always have to be working out, because in sometimes the non-interacting reference point is not the right reference point. Just example, if you have like some interactions can lead to magnetism or superconductivity. Now if you take a superconductor and say, well, let's consider we have a non-interacting electron gas, or make then some perturbation theory around like superconductivity, or the BCS theory, it's just that you have some attractive interaction which is transmitted by exchange of lattice oscillations, which leads to an effective attractive interaction between the electrons. Now you could say, well, let's just consider the non-interacting electron gas and then consider what happens perturbatively to the non-interacting electron gas if we add the small, very small attractive interaction. There what we will see actually is that there is instabilities, this kind of collective instabilities going on. And this just reflects there, in this case, that, well, the non-interacting ground state is just the wrong ground state that you did, that you try to evolve your theory around, because we know that however weak the attractive interactions are, they will lead to some very different ground state, which now carries a superconducting condensate. Okay, so there's some totally different ground state. And this actually typically is reflected in such kind of collective instabilities if you do the perturbative analysis around the wrong ground state, that you see that some kind of collective instability is going on. So this we will see, but then we need some different scheme how then to deal with the problem. So we have to find some systematic way. If we have a problem, well, what is the right ground state? How do we identify the right ground state, and how to then formulate like the perturbation theory around this? And all this leads to the idea of effective theories that maybe we can still start a little bit and then continue like next week, which is like a more systematic way than what we did so far. So there were some assumptions going on here which do not always have to be the right ones. And maybe just make 5 minutes break and then we continue with the next week.